So it is my great pleasure to introduce Dr. Adrian Price-Whelan. He's our presenter for tonight from the Flatiron Institute and has worked with our team to come up with a beautiful realization of his work on the dome in terms of dark matter and how you ever learn anything about something you can't see. He has a PhD from Columbia. I just learned that he has a background in theater tech. So a very well-rounded individual. I'll hand things now over to our wonderful presenter, Dr. Price-Whelan.
Mike, there I am. Okay, cool. Yes, so I dressed both in all black because the theme is dark matter, but also because my background is in tech theater, so this is the only clothes that I know how to wear. Good, I think we can turn me off, because again, tech theater, I never want to see myself at the front, and instead, we're gonna start to explore the universe. And so the theme, by the way, I wanna say to start here, you probably think I do this all the time, like stand in a planetarium and look at things like this, but this is my first time actually seeing data and simulations and work that I've done projected onto such an amazing screen. So for me, I'm gonna be standing up here going, what? The same that you are in the audience, I hope. So anyway, today we're gonna be talking about dark matter, as Mike alluded to, and that's a pretty esoteric and weird thing to think about. It has basically no impact on your day-to-day life. I've always wanted there to be like a space echo when I say like dark matter, like that. But anyway, so we're gonna be talking about dark matter. It's a weird thing. We're not gonna start there. We're gonna get there. We're gonna start instead with something more familiar to you. And so we're gonna start with New Jersey. Hopefully that's at least familiar to you. So you're sitting right here in this dome. You probably recognize some of the landscape here. And just to orient you on the types of sizes and length scales that we're going to be talking about, we're going to start in New Jersey and zoom out into the universe. So this is what you're used to from day-to-day life. We can start zooming out a bit. You're used to maybe driving on roads like this, where you think of things in terms of miles, things that are miles away, takes hours to get there. As you zoom out, you're probably still familiar with this scale. You fly across the country or you fly around the globe. You're used to thinking in terms of thousands of miles, probably. It takes a couple hours on an airplane to get a few thousand miles away, for example, to LA or California. So when you look at the face of the Earth, now we've departed New Jersey and the Earth. We're looking at the whole sphere of the Earth, North America here. The size of the Earth, just to have a number in mind, is typically measured in terms of tens of thousands of miles. So the circumference of Earth is about 24,000 miles in size. And so we're going to keep going, we're going to keep zooming away, and I'm going to keep giving you reference points in terms of sizes until we get to the point that I'll be talking about. So as we zoom away, we leave the Earth even more, and at some point, other planets and objects are going to come into focus. So now we see the Earth here moving around the sun, which is at the center. There's other planets, Mercury, Venus, Mars, etc. And already there's a big jump in terms of the number of zeros we have to keep track of. On Earth, you're used to miles or thousands of miles. Now we have to think in terms of hundreds of millions of miles. So the Earth is about 93 million miles away from the sun. And astronomers are sort of lazy. We don't like to keep track of all those zeros all the time. And so instead of saying 93 million miles, we define a new unit, a unit of measurement called the astronomical unit. And in those units, we can say Earth is 1 astronomical unit, 1 AU away from the sun. And that's the typical size or length scale to think about in terms of the solar system, where all the planets are, like the Earth. Mars is a little more than an AU away. Even the outer planets, don't even know what is that, Jupiter? Saturn. Saturn is just a few AU. So that's the typical scale of the inner part of the solar system. But now if we zoom out a bit more to the next stage, away from the inner parts of the solar system, this is going to be a theme, by the way, we rapidly get to a point where we have to deal with a lot of zeros again. So now we get out to the very outer reaches of the solar system. This is all of the points that you see here are comets. These are the things that make headlines occasionally as they fall into the inner parts of the solar system and get heated by the sun. They have these beautiful tails. This pool of comets at the very outer edge of the solar system is known as the Oort cloud. And the typical size of the Oort cloud is about 100,000 astronomical units, 100,000 times the distance between the Earth and the sun. So astronomers are lazy. That's a lot of zeros to have to write down and keep track of all the time. And so we again define a new unit. And that unit is called the parsec. And some of you, raise your hand if you've heard of the parsec before somewhere. Yeah, a few of you, from Star Wars probably, where it's incorrectly used as a unit of time. It's actually a unit of length. And the typical size of the Oort cloud, the furthest area around the solar system where the sun's gravitational influence matters, is about one half of a parsec, 0.5 parsecs. And that's a useful unit of measurement, the parsec, because we don't then have to say 200,000 astronomical units, we can just say 1 parsec. And that is also useful because it's the typical distance in between our sun, which is at the center of this cloud, and all of its neighbors. So it's typically about 1 to a few parsecs away from the closest, the most nearby stars around the sun. Okay, so we're at parsecs, individual parsecs, but we can, of course, keep zooming out away from the solar neighborhood, as we say. And now we're going to see the scale of a galaxy. So the sun is sitting about here. This is a representation of our home, the Milky Way galaxy, which I've always thought is kind of a gross and unfortunate name for something so amazing. But anyway, this is the Milky Way. This is a representation of the Milky Way. And as I mentioned before, the theme is we've gone up another level in terms of scale, and now we have a bunch of zeros again. Parsecs are the typical scale, the distances between the stars. The size of the Milky Way galaxy is about 30,000 parsecs, which is billions of AU, astronomical units. So that's just too many zeros. And so now we don't redefine a new unit to talk about the sizes of galaxies. We just start using the prefixes, SI prefixes, that you might be familiar with when thinking about grams and kilograms. 1 kilogram is 1,000 grams. We use the same prefix when we're talking about the size of a galaxy. We say that it's about 10 or 30 kiloparsecs. So that's 30,000 parsecs across. But we can go further. So we can leave our galaxy, we can depart the Milky Way, our home galaxy, and think about the universe. Because of course, we're just one galaxy in a sea of billions of other ones. And now we've gone up another level in terms of length and size. And now galaxies themselves tend to be separated, unless they're merging like these ones here, galaxies tend to be separated by about 1,000 kiloparsecs. So now we can use another SI prefix, which you might be familiar with from thinking about kilobytes and megabytes and gigabytes. And so now we can say that galaxies tend to be separated by about 1 megaparsec, 1 million parsecs. So that's the typical separation between galaxies. For example, the Milky Way is a little bit less than 1 megaparsec away from our nearest big neighbor, the Andromeda galaxy. And that's the typical scale you should think of. The entire observable universe is one level above that. We're not going to go there, but it's gigaparsecs, billions of parsecs in size. And from studying the locations and the motions of all of these galaxies that we see in the universe, we've been able to come up with a model, a cosmological model, that lets us understand the composition of the universe on these very, very large scales. So for example, if we could pull up that plot, we know that most of the universe, in terms of the energy content of the universe, is made up of this totally mysterious thing called dark energy. And this makes up about 2/3 of the energy of the universe. This is what's driving the acceleration of the expansion of the universe. It's like it's a repulsive force, you can think of it like that, that's driving the speeding up of the expansion of the universe. And we have no idea what this is, but we just see it in terms of how fast galaxies are moving. An important thing to note is there's another mysterious thing that makes up the second most dominant component of the universe, and that's dark matter. Dark energy and dark matter make up most of the energy in terms of what's present in the universe. And all of the ordinary matter that you're used to, the atoms in this room, the air that you breathe, whatever makes up your shoes and iPhones and whatever, all of that stuff is just a tiny fraction of the total contents of the universe. And so I just want to emphasize that this is a small fraction of the total pie. Dark matter is a larger fraction, and dark energy is the largest component of the universe. But I get sort of uncomfortable when I think about very, very large scales in the universe, especially on the scales of billions of galaxies. And it's on those scales that you have to worry about dark energy. I'm a little bit more comfortable thinking about individual galaxies instead. To me, those are finite-sized objects. If we go to the next slide. Those are finite-sized objects. They're smaller than, we talked about how they're 30,000 parsecs. They're measured in tens of kiloparsecs in size. When we study an individual galaxy, we don't have to worry about all of the things that operate on very, very large scales in the universe. So for example, we can actually ignore the whole contribution of dark energy when we're studying individual galaxies. So this is an image of a representation of the Milky Way that we saw before. I want to emphasize one thing. This is not the Milky Way. We don't actually have an external image of our own galaxy. Because those length scales are so long, at our current fastest spacecraft, Voyager, it would take about 200 million years for it to get to a height above the galaxy high enough to get a picture like this. So we're never going to have an image of our own galaxy from this perspective. So if you ever see an image like this that says the Milky Way underneath it, it's usually a simulation or someone's lying to you. But let's pretend for now that this is the Milky Way. We're going to use it as a sort of stand-in. The Milky Way is a fairly typical galaxy. It's a disk galaxy. It has these spiral arms. In terms of the stuff we can see, it's mostly made up of stars and gas, of the luminous components of the galaxy. So we think there's about 100 billion stars in the Milky Way. I don't exactly know the number. Nobody really does. And that's actually one of the reasons I like astronomy, is that nobody's life depends on me knowing that number to an extreme precision. So it could be 70 billion or 110 billion. I don't know. It's around 100 billion. And one of the interesting things is that most of the stars in the galaxy are actually much lower mass, are smaller than our sun. So our sun is actually slightly bigger and more massive than the majority of the stars that exist in our galaxy. So a lot of the light and the luminous stuff that you see here is stars, but there's also a lot of gas. And most of that gas is incredibly boring. It's just hydrogen, which is the first element on the periodic table. One proton, one neutron, one electron. And the reason most of it is hydrogen is because at the very early part of the universe, that's basically the dominant thing in terms of ordinary matter that was formed. All of the other kinds of matter that you know about, the other elements like carbon and nitrogen and oxygen, all of those elements predominantly were formed in stars. They were formed later on after stars formed from the hydrogen and then fused that hydrogen into helium and heavier elements. So there's a little bit of those other elements here, but predominantly most of the gas that we see in galaxies like our own is just hydrogen, pretty boring. So those are the luminous components, the things that we can actually see, the things that are more similar to the stuff that we interact with on day-to-day life. We see the sun typically every day, unless you live in Rochester, where there's clouds. But anyway, there's one of the interesting things that is the subject of this talk is that we also think there's a lot of some other substance present in galaxies like the Milky Way. And we call that substance dark matter. And so the dark matter, which we're going to represent just as a sort of purple haze here, the dark matter, we think, permeates through the entire galaxy. We can't see it. It's totally invisible. And we think it vastly outweighs the luminous matter that we see. All of the stars and the gas added together is a small fraction of all of the dark matter that we see. So I want to talk for a minute about why we think there's this invisible stuff in galaxies. We can see stars and gas. How do we know that there's all of this other stuff also there? There's many different lines of evidence for this. I don't have time to go through all of them, so I'm just going to give you two of my favorites, which are two of the earliest pieces of evidence that have been used to build up our understanding about what we now know about dark matter. The first of those lines of evidence I want to talk about is the rotation speed of galaxies. And so to understand how you can use the speed that galaxies rotate in order to study mass or the existence of this invisible stuff, it's useful to think of an analogy. So we're going to think about the solar system for a second, because you might think it's kind of like a miniature galaxy. Instead of stars orbiting in a galaxy, we have planets orbiting a star. And they do so in roughly a planar configuration. So if you looked at the solar system edge on, it would look very flattened, kind of like a pancake or a record as the planets are orbiting. So you can kind of think of it like a miniature analog to a galaxy. And what happens in the solar system? Well, the planets that are closer to the sun feel much more gravity from the sun. And so they have to move very fast in order to maintain the orbits that they're on. What you can see if you just track with your eye these other planets as they're further away from the sun, is that the ones that are further away don't have to move as fast. And that's because they're further away from the sun, they feel less gravity, they feel less of the gravitational influence of the sun, and so they don't have to move as fast in order to maintain an orbit. And so, for example, Jupiter here is moving fairly slow compared to the orbit of Mercury. Another way to look at this is with a plot. Scientists love diagrams like this. I've tried to make it very simple here. This is a figure or a plot that shows the speed of a planet, so slower here, faster here, versus the distance that a planet is from the sun, so closer to the sun, further from the sun. And what this is supposed to emphasize is that planets like Mercury, Venus, Earth, those are closer to the sun, and they move faster, they're higher on this axis compared to the outer planets like Jupiter and Saturn. And so our expectation from what we understand about gravity and how things orbit is that if you did an analogous experiment in a galaxy and you measured the speeds of stars, we could go to the next slide. We measured the speeds of stars at different locations in a galaxy, like each of these points here in this rainbow. This is the Andromeda galaxy, by the way. So if we're able to pluck out a star at each of these points and measure how fast it's moving, what we would expect to see is, we could pull up the plot now. We'd expect to see that the blue points, for example, should be moving slower than the purple and the red because they're further away from the center of the galaxy. And what's really interesting is this was a discovery made by Vera Rubin, who was an astronomer working in the 1970s. She found that in any galaxy she looked at, she instead saw, you could click there, that no matter what distance she looked at the speed of a star away from the center of the galaxy, roughly, they all moved with about the same speed. And so the conclusion from this was, well, there must be some other mass, some other matter involved that's making it so that the stars that are further away from the center of the galaxy have to move faster in order to maintain their orbits. So this was a very convincing and early piece of evidence for the existence of this other substance known as dark matter. So that's one line of evidence I wanted to mention. A second line of evidence I want to mention is a phenomenon known as gravitational lensing. So we're going to see an image here. This is an image that was taken and released last year by the newly launched James Webb Space Telescope, JWST. And this image shows this phenomenon, which is known as gravitational lensing. So what is this lensing thing? So what do we see here? So there's a bunch of galaxies. Some of these galaxies are close to us in astronomical terms, like this one right here, right at the top, or this one here. These are closer to us. And some of the galaxies are much further away, like the one that's smeared out here into a blob. The fact that some of these are smeared out is an indication that this process of gravitational lensing is happening. So what is this phenomenon? This was actually a prediction from Einstein's theory of general relativity 100 years ago, over 100 years ago, which is the idea that if you have very massive things in the universe, they actually act to distort the path that light takes. So light would move in a straight line, but if you put some mass in the way, the light will bend around that mass. And that's very similar to what happens with an ordinary lens. So for example, if we could pull up the horrible image I found on Google, if you shine 3 parallel beams of light into a normal lens, this lens distorts the path that the light takes. So it comes in parallel and it comes out where the beams are going at different angles. The same thing happens with very massive galaxies in the universe. If we could go to the next schematic here. If you have some very, very distant galaxy that looks like a normal disk galaxy, like this one here, and you put a big galaxy in between us and that galaxy, it distorts the path that the light from that galaxy takes into very weird, distorted images. And the interesting thing is, if you go to the next slide, because this is a core prediction of general relativity, so this is again the schematic here, the Earth, there's a galaxy close to us and a galaxy further away, because this process of this light bending around the mass as it comes to us, this is a prediction of general relativity, we can actually just measure how much the light is bent, plug it into some equations, and calculate the mass of the object that's in between us and the distant galaxy. And so this gives us a way of measuring mass in the universe. And one of the interesting things that we found very early on, some of the first confirmations and observations of this process were, again, in the 1970s, confirming the prediction from general relativity. What we saw is that the mass required to bend light as much as we see it is much, much larger than the sum of all of the stars we see in these intervening galaxies. So we need a lot of extra mass in order to explain how much the light is being bent. So this was another very clear evidence for a piece of evidence for dark matter. So we can go to the next slide. So now I'm just going to show you a couple pretty images of these real gravitationally lensed galaxies. This is an example where the two galaxies are basically lined up. So this galaxy is closer to us. This blue thing would look like a normal galaxy, except that it's way behind this foreground galaxy, and so it gets distorted into this arcing thing that we call an Einstein ring, named after Einstein for his theory of general relativity. By the way, you can actually simulate this exact process with the bottom of a wine glass. So if you ever break a wine glass, save the bottom, and you can make your own gravitational lens. Anyway, so this is from the Hubble Space Telescope. We're now totally spoiled. We have images from the James Webb Space Telescope. So the next one is a zoom in from that first image I showed of this totally bizarre, distorted galaxy here. This is because it's being lensed by this foreground galaxy. Show the next one. Another typical thing you see is these very arcing, weird features. You go to the next one. Oh, and then actually to the next build. And so now I want to show you just one last image in the theme of gravitational lensing, because this is hot off the press. This is an image that came out, I think, about a week ago from the James Webb Space Telescope. And this just totally blew my mind. This was a galaxy that would otherwise look like a normal disk galaxy like the Milky Way, but because of this pesky foreground galaxy, it's distorted into this totally bizarre shape and strange image. And there's similarly weird things happening to other features and arcs that you see. So this is beautiful, beautiful demonstration of JWST, James Webb. Cool, so we can go to the next image. So we just talked about two pieces of evidence for the existence of this dark matter. Both of them I mentioned offhand were made in the 1970s. So you might be wondering, that was 50 years ago. Surely we must have figured out what this stuff is by now, right? It's 2023. And unfortunately, we still have no idea. So it's still a huge mystery. And one of the reasons it's a mystery is because it doesn't seem to be made of ordinary matter. It doesn't seem to be made of electrons, protons, neutrons, all the things that you're used to thinking about, or maybe have thought about at some point in the past. And so that means we can't just build a detector and look for the collisions of dark matter with the detector. We can't directly see the particles. And so the whole business of trying to study dark matter, we can only do it astronomically. And that's a very indirect way of doing it. We can't set up an experiment and run the experiment. We just get what the universe gives us. So the main way that we've made progress over the years is particle physicists will sit in a big chair somewhere in front of a fire and think of their favorite crazy ideas for what could explain dark matter. They write down a theory. We then, as astrophysicists, take those theories and we run a big simulation to try to predict what the implications of that theory is for the structure of dark matter on astronomical scales. We then go out and we look for observations that can confirm or rule out those predictions. So I just want to give you a sense of the kinds of theories people think about and the implications for how dark matter is structured on the scale of galaxies. So you could pull up the next, you're ahead of me. Great. So these are 3 simulations, numerical simulations we can run on a computer, a big computer, of 3 different theories of dark matter. These are just the names we give them. You can call them whatever you want. So what's shown in these images is the predicted structure of dark matter around a galaxy. So a galaxy like the Milky Way would sit right at the center of each of these images if one of these is the correct theory. And this is the prediction from the theory of how the dark matter is distributed spatially around a galaxy. Just to give you a little bit more information, this cold dark matter, this is a theory where the particle that makes up the dark matter in the very early universe starts off very slow. And so it can condense and collapse through gravity into these very small clumps that you see here. Warm dark matter is similar, but instead of starting out very slow, the particle starts out with a little temperature, and that causes the particles to jiggle around a bit. And that jiggling means the particles that make up the dark matter never condense or coagulate into very, very small clumps. They're too excited, they're too jiggly. And so you erase a lot of this substructure. You can see the broad properties are roughly the same between these two. There's a dense bit of dark matter at the center, and it gets less and less as you go out. But between cold dark matter and warm dark matter, you remove a lot of these clumps. And a similar thing is true for this other theory, this interacting dark matter, which is a theory where the particle that makes up the dark matter can collide with ordinary matter at a very low level. And that also has the implication that it erases substructure. So this is a thing that normal atoms do. Like the reason we have wind is because atoms collide into other atoms and drive the blowing wind. That kind of process could happen in this theory at a low level. So this is the kind of thing we have to do, and then we have to look for telltale signatures within these predictions or these simulations that can allow us to distinguish on astronomical scales between these different theories. And one of the things you might notice from looking at these 3 is they predict very different amounts of substructure, little clumps of dark matter. They're everywhere in cold dark matter at all scales. There's a couple, they're fewer in number in warm dark matter, and there's basically none in this other theory. And so the name of the game right now, and in some of the work that I do, is to try to develop methods and then go out and look for these clumps of dark matter. And one of the ways we want to do this within or around a galaxy like our own, the Milky Way, is to use the motions of stars. And the reason we have to do that is because we can't rely on gravitational lensing or any other method that we have that operates on very large scales, because these little clumps of dark matter are too small to appreciably distort the images of galaxies. So the only way we know to look for these things, if they exist, is to look for very slight distortions and anomalies in the way that stars are moving around the Milky Way. And one of the challenges there is timescales. So we talked about the solar system. As you are probably aware, it takes about a year for the Earth to go around the sun. So the timescales over which the planets move and orbit, you can just watch Mars change its location over the course of a year on the sky. That operates over human timescales. Well, what happens on galactic timescales? If we want to see stars moving, Unfortunately, it takes stars hundreds of millions of years to do the same thing, to orbit around a galaxy like the Milky Way. So we could go to the next build. So for the sun, the last time it was in the position that it is now was about 250 million years ago. And that was the Triassic period, which is when the first mammals were coming into existence. So it looked like a very different Earth back then, and basically is an irrelevant timescale for humans, right? And so if we want to be able to measure the motions of stars and little anomalies in their motions over human lifetimes, we have to have an incredibly precise instrument. And luckily, we have such a thing. It was launched on a satellite, a spacecraft known as the Gaia survey, the Gaia mission. And Gaia, this is not to scale, by the way. This is the Gaia satellite here. Gaia is orbiting far beyond the orbit of the moon, following the Earth around as it orbits the solar system. And as it does this, it's constantly scanning the sky. And it scans the sky, I think, every 90 minutes. And it records, it has one job. It records the location of every star it scans very, very precisely, very accurately, every time it completes one loop, one cycle. And then it just does that over and over and over again. It's been running for about 10 years. And what we get from this survey are incredibly detailed, fine measurements of how stars are moving. The precision of this instrument, by the way, is equivalent to measuring the rate of human hair growth of someone on the moon from Earth. So it's just absurd. Like the fact that we can build an instrument like this and launch it and have it stably do its job is amazing to me. So one of the things we get from this mission is we now know where all of the stars in our little neighborhood of the Milky Way are moving. So it's measuring those motions for about 2 billion stars. That's actually a small fraction of the total number of stars in the galaxy, but it's still very helpful. So if you go to the next build, so it tells us, let's see them move, tells us now where the stars are going. So we can now predict in 10,000 years where will Betelgeuse or Sirius or Rigel be, and many other fainter stars, about 2 billion of these stars in the Milky Way. Cool, so we have these incredibly precise measurements of the motions of stars in the Milky Way, in our galaxy. How are we going to, remember our task is to find these small clumps of dark matter, because that's going to allow us to distinguish between these different theories that we have, predictions from these theories on astronomical scales. And the way we do it is with my favorite kind of astronomical object, which are known as stellar streams. So now we're going to zoom out again and look at the galaxy. So this is the Milky Way, and around it are hundreds of objects known as stellar streams. So we can turn those on. And so to understand what these are, I want to connect them to an object that you might be more familiar with. Raise your hand if you've heard of a star cluster before, or the Pleiades, things like that. Okay, so a fair number of people. Raise your hand if you've heard of a stellar stream before. Cool. They're almost the same thing. So so a star cluster looks like the next build. The star cluster looks like a big ball or collection of stars that are all orbiting one another. They actually shine despite the darkness. So a star cluster is a big ball of stars that are all orbiting one another. And they're orbiting one another as the whole star cluster is orbiting around the Milky Way galaxy itself. So we know of many of these star clusters, hundreds or even thousands of them that exist around the Milky Way. They have names like the Pleiades. There's a bunch of Messier objects. You might have heard of M92 or M10. They also have other random names that astronomers like to give them, like NGC 1712 and blah, blah, blah. We're working to get them up. If not, we can just skip to the next build, that would be fine. Cool. So we know of hundreds and even thousands of these star clusters. All of these little yellow points and red markers are representing star clusters that we know of around the Milky Way. And they're not static. Over hundreds of millions of years, they orbit around the Milky Way just like the stars do. And as they orbit around, some of them survive and remain happy and happily bound in these little balls. Other ones are less fortunate. Other ones feel too much of the influence of the Milky Way's gravity, the gravitational field of the Milky Way, and they get torn apart. And as they get torn apart, the stars that were once in one of these star clusters get stretched out into a long, arcing stream of stars. And these are the stellar streams that I mentioned before. So we could turn the streams back on. They're really like rivers of stars. They're former star clusters where now all of the stars in a stellar stream just move along in the same direction, flow in the same direction, with roughly the same speed, almost the same speed. So these things continue to persist and orbit around on the orbit that they used to be on when they were a star cluster. So why am I talking about these stellar streams if we want to find little clumps of dark matter? Well, if you've ever had a hose in one hand and put something in front of the water coming out of a hose, or if you've ever thrown a rock into a river or a stream before, what does it do? It causes a big splash. And the same thing happens if you have a clump of dark matter and it flies through one of these streams of stars. It creates a splash, and it causes the stars to spread out from a particular part of one of these streams. And that leaves an imprint on the stream that we can then go and look for. And if we see many of those things, it tells us that the dark matter has to have these clumps. And so therefore, that informs us about the theories that we have for dark matter. So I have the last thing I want to show you is a simulation of that process. So this is a computer simulation of one of these stellar streams orbiting around the Milky Way galaxy. And at some point, one of these clumps of dark matter, represented by this purple sphere, it's going to hit a part of the stream, and you're going to see what happens. So here's one of these streams of stars. Because this is a numerical simulation, we can actually play it forward in time. We can predict exactly where those stars are going to be. So we could start the simulation. So right now, the dark matter clump has not hit the stream yet. I'll tell you when it does. It's just orbiting very close to the stream. And I think around now, see, it hits the stream, and it opens this gap, and it causes the stars to spray away, very similar to if you threw a rock into a very fast-moving river. And so this process where a clump of dark matter can hit a stream and leave a gap and leave these other features is exactly the kind of signature that we need if we want to be able to find these small clumps of dark matter. And that's the core basis of a lot of the work that I do. The exciting thing is we think we've actually seen this imprint in two stellar streams that we know of around our galaxy, around the Milky Way. They have pretty boring names. One's called GD1, and the other one is called Atlas. But there's many streams. There's a whole zoo of names of these stellar streams. We hope to find more of these signatures, but already the fact that we've seen this imprint in two streams tells us that whatever the correct theory for dark matter is, it has to be similar to cold dark matter. It has to make those very dense clumps of dark matter that can interact with these streams like a stone thrown into a river. So that is where I want to end. I want to say dark matter is still one of the biggest outstanding questions. The nature of dark matter is one of the biggest outstanding questions in astronomy and in physics research right now. I think that it's a big challenge to study it because it doesn't interact very much with ordinary matter. But thanks to this amazing data from missions like the Gaia survey, we now have these new tools that we're armed with to look for signatures that can help us distinguish between these different theories for dark matter. And so hopefully I can come back in 10 years and tell you that we shine the light on dark matter and we now know what it is. But right now it's still a mystery.
All right, thank you so much, Dr. Price-Whelan.